In this video, we'll look at the standard normal distribution. In the text, you're provided with an equation, equation 311 for the standard normal distribution. We're not going to use that equation. We're going to use Excel to find the probabilities of a value. The text talks about Excel. It also shows you how to use a table to find the cumulative probability of a value. We don't use tables very much anymore. We have Excel and other applications now that do the lookup for us. It's much more efficient. You should read through the chapter in the textbook and learn to use the table, but I'm not going to talk about that in the video. The standard normal distribution is the distribution that has a mean of 0 and a standard deviation of 1. And in a normal distribution, that would mean that the mode and the median are also 0. So mean, median, mode of 0 and a standard deviation of 1. The text, it has us find the cumulative probability for a value of z. The z that we're provided with is negative 0.85. What we want to find is the cumulative probability for a z value of negative 0.85. In other words, the area under the normal curve to the left of minus 0.85 standard deviations, z of minus 0.85. To calculate that in Excel, we use the standard normal distribution function, and that is norm.s.dist. And it asks for the z value, which is minus 0.85. And we're always going to answer true to the cumulative question. We always want the cumulative value, in other words, the values to the left of our z value. In a continuous distribution, remember, the probability of an exact value, so exactly 0.85, is 0. In a continuous distribution, equals doesn't have a meaning. We can look for less than or equal to 0.85 or less than 0.85. Those are the same values, unlike a discrete probability distribution where you can find the probability of an exact value. So we'll go ahead and press enter here. We find that that probability is 0.197. And if we were to look at that on a graph, we would see this shaded area here represents the area under the curve to the left of minus 0.85. So 19.77% of the area is to the left of minus 0.85. Next, the text gives us a z value of 1.25. So now we're going to go on the other side of the mean. Minus 0.85 is to the left of 0. The mean in a normal standard distribution, the area of the curve to the left of 0 is 0.5, the same as the area under the curve to the right of 0. So let's go ahead and calculate the new value. We'll take that out. Put in 1.25. That's the new z value. Let's calculate that in Excel using norm.s.dist. Again, we want the z value. Again, we're going to answer true to the question, to the cumulative question. Press enter. We see that we have 0.8944, or 89.44%. of the area under the normal curve lies to the left of 1.25 standard deviations, or a z of 1.25. If we were to place that on our chart, we would see 1.25, and the area here to the left is 89.4% of the area under the curve lying to the left of 1.25 standard deviations. Now, even though the probability of a exact value is 0, we can find the probability of a range of values. So instead of just finding the area to the left of a value, we can find the area between two values, and the text gives us a z of -1 as the lower z value and a z of +1 as the upper z value. So let's go ahead and calculate those with z equals 1 as the upper and z equals -1 as the lower. So the probability that z is greater than -1, but that z is less than 1. I'll begin by calculating the area under the curve for s.dist to the left of a z value of 1, true, to the cumulative question. Then I'll find the area under the curve, s.dist, to the left of a z value of -1, true, cumulative question. Then I will subtract from the larger value the smaller value, and that gives me 0.6827. That is the area under the curve between a z value of 1 and a z value of -1. If we were to illustrate that on our chart, we would see the shaded area here beginning at a z value of -1 to a z value of +1. This represents 68.27% of the area under the standard normal distribution curve. The text continues with a section on computing probabilities for any normal distribution. It's very rare that we would come across a distribution that has a standard deviation of 1 and a mean of 0. Normally, they are real-world numbers. There is an equation that we use to convert our real-world values into the z-score. Z equals the value we're looking for minus the mean of the distribution that we have all over the standard of our real-world distribution. The text uses the example of the Greer Tire Company. The Greer Tire Company has developed a new steel-belted radial tire that will be sold through a national chain of discount stores. From actual road tests with the tires, the engineering group has determined that the mean tire mileage is 36,500 miles. So we will enter 36,500 for our mean, and the standard deviation of 5,000 miles. They want to know about the performance around an X value of 40,000 miles. So let's compute a couple of things. Let's first of all calculate the percentage of tires, the probability that the tires will last at least 40,000 miles. At least 40,000 miles. 40,000. The probability then that X is less than 40,000, we have to first calculate the z-score, and that will be our X minus our mean, and we'll place that over our standard deviation. That gives us our value of z. Now we can use the normal standard distribution with a z value of 0.7 and a cumulative of true to calculate the probability that the tires will last at least 40,000 miles, and that's 75.8% or 0.758. Well, let's ask this another way. We'll take this out and take this out. Let's ask the probability that a tire will exceed 40,000 miles, will last more than 40,000 miles. All right, the same process here. We're going to find our Z value. So we'll take our X, we'll subtract that from our mean. We'll take that quantity and place it over our standard deviation. That gives us our Z value again. This time, we don't want the area to the left of 0.7, the cumulative value. We want the area to the right. We know that the total area under the curve equals 1. So if instead of just calculating norm.s.dist for a Z value of 7 and true to the cumulative question, if I take 1 minus norm.s.dist, Z value of 0.7 true, I'll get the value to the right, so 0.2420, 24.2%. Now if we were to put these two calculations on our graph, we would see that for the less than 40,000 miles, or at least 40,000 miles, we have 75.8% of the area under the curve. And for greater than an X of 40,000 miles, or more than at least 40,000 miles, we still have a Z value of 0.7, but we do 1 minus, and we get the area to the right of 0.7, and that is 24.2%. Now to carry this a step forward, let's say we want to know the probability that our tires will get between 37,000 and 40,000 miles. So we have an upper X value of 40,000 miles and a lower of 37,000. Now again, we need to calculate our Z values. We have the probability that X is greater than 37,000 and that X is less than 40,000. So we'll take the calculate the upper Z score, and that will be our upper X minus U all over our standard deviation. Then we calculate our lower Z value, which equals our lower X minus mu all over our standard deviation. We'll go ahead and calculate the area under the curve to the left of a Z value of 0.7. True, the cumulative area. Then we'll calculate the area under the curve to the left of a Z value of 0.1. True. And then from the upper bound, we will subtract the lower bound, and that gives us 21.82%, or 0.2182 is the probability that our tires will get between 37,000 and 40,000 miles. If we were to show that on our graph, we would see this area between 0.1 and 0.7, representing 21.82% of the area under the curve. These are some examples of how you use the standard normal distribution and the Z-test to find the area under the curve for values that meet the conditions of the standard normal distribution, in other words, a mean of 0 and a standard deviation of 1, but also using the z-test for real-world values where we might have calculated a mean or a standard deviation that applies to our process, and then we want to know something about that distribution.